This is your presenter Asloop Mudassar, and I am presenting slide number 133 of the course on laser physics. Question is, what is an active mode locking? Give the types of important active mode locking techniques. Discuss the amplitude modulation, that is AM based active mode locking technique in detail, which is regarded as the most important technique. Also briefly describe the less important frequency, that is FM modulation technique. The answer is, in active mode locking, a device is inserted into a laser cavity which is driven by an external voltage source. If the device modulates the amplitude of the oscillating modes to achieve mode locking, it is regarded as an amplitude modulator, briefly AM, and the technique based on AM is known as amplitude mode locking. If the device modulates the phase of the oscillating mode, it is regarded as the phase modulator, and the technique is known as phase mode locking. If the device modulates the gain of the laser medium with a repetition rate delta nu equal to C over 2L, the device is known as the synchronous pumping. You see that here the cavity modes we are talking about are actually the longitudinal modes. We have had a great discussion on the topics of longitudinal modes, and we have also a discussion on the mode locking in the previous slides. Here we are going to discuss the active mode locking devices, which are amplitude mode locking and frequency mode locking devices will be discussed in detail. And the modes, you know that in the laser, the longitudinal modes are separated by a spectral distance delta nu, and delta nu is equal to C over 2L, where L is the length of the cavity. So all the longitudinal modes are separated by this distance delta nu. So we have the central mode, then we have the side modes on either side. For example, if the central mode is Q, then on the right we have the Q plus mode, on the left we have the Q minus mode, and similarly the next modes are Q plus 2 modes, and on the left hand side we have the Q minus 2 modes. So these are the longitudinal modes. First, we discuss the amplitude mode locking technique. Consider a cavity mode Q oscillating in a laser cavity at a frequency omega q. Initial phase phi q measured with respect to the central mode, whose phase is regarded as 0, and the amplitude is E naught. So you see that now we are considering only a cavity mode, which has been labeled as the Q mode of the cavity. And the mode will oscillate with the frequency omega q. The initial phase of the mode will be phi q, and the amplitude of the mode will be represented by E naught. And you know that if we are considering a mode q, then this phase which we are talking about as a phase q, this is the phase of the qth mode which has been measured from with respect to the central mode, because we are here regarding the central mode as the mode with a 0 phase. That is the central mode, the phase of the central mode is acting as our reference phase, and we are regarding the phase of this mode to be the 0 mode, and all the modes of all the other and the phases of all the other modes will be measured with respect to the central mode. So here we are considering that Q is any mode, and its initial phase is phi q with respect to the central mode. This mode is oscillating with the frequency omega q, and the mode has an amplitude equal to E naught. If an amplitude modulator is placed in a cavity with the modulating frequency omega m, with an amplitude modulator factor 1 minus delta, where delta is the depth of the amplitude modulation, then the electric field of the qth cavity mode can be written as. So you see that as discussed earlier that we are talking about the qth mode. And now we are also talking about amplitude modulator placed in the laser cavity. This amplitude modulator is oscillating with a frequency omega m. So that's why m stands for the modulating frequency. So this modulator, that is the amplitude modulator, is modulating at a frequency omega m. And with the amplitude modulating factor is 1 minus delta, which I shall explain later. And delta is the depth of the amplitude modulation. Then the electric field of the qth cavity mode can be written as. So EQ as a function of time is equal to E naught into cos of omega t, omega q into t plus phi q. And this term in red is due to the presence of the modulator, of the amplitude modulator, because we are talking about amplitude modulator here. So if the amplitude modulator is not present in the laser cavity, then of course this term shown in red will not be present. And only this would then be the amplitude or and the qth mode of the cavity will then be governed by this electric field, that is EQ as a function of time will be equal to E naught into cos of omega qt plus phi q. But in the presence of the modulator, we have this additional term shown in red, where omega m is the frequency of the modulating frequency of the modulator. So you see that if you consider this 1 minus cos of this actually becomes a more or less equal to a sine function, because you see that initially when time is equal to t is equal to 0, this cos becomes 1, but 1 minus 1 becomes 0. So it means that 1 minus cos of omega mt will effectively appear to be as a cosinusoidal function. And the amplitude factor is this one, which will control the amplitude of this sinusoidal function will be controlled by 1 minus delta. And the delta is the depth of the amplitude modulation. So you see that if you set the value of delta equal to 0, even then this will vanish out. That is, the amplitude modulator will vanish out. So in order to have this amplitude modulator to have the maximum possible value, we can set the value of delta to be close to equal to 0, so that we can have this factor can have a maximum magnitude equal to 1. Otherwise, the magnitude of this 1 minus cos of omega mt can be controlled by 1 minus delta, and in principle by the value of delta. So delta can take any value in the interval, that is delta could be the minimum of delta will be 0, the maximum value of the delta will be equal to 1, and the delta can lie anywhere between 0 and 1. Now you see that you can expand this term, that is you can multiply these terms inside this one, that is you can split this parenthesis that contains 1 minus cos of omega mt. So due to 1 we have one factor, and due to cos of omega mt we have the second multiplicating factor. So the first factor is this one, which is by the multiplication of 1, and if you multiply the rest of the terms with the cos of omega mt, you have this term, that is E naught into 1 minus delta into cos of omega mt multiplied by cos of omega qt plus phi q. But you see that now we are going to expand this second term. This second term can be trigonometrically proved to be equal to cos of omega mt times cos of omega qt plus phi q if you multiply it with the 2, and also you need to divide it 2 with over here, so the rest of the factors will be divided by 2, that is E naught into 1 minus delta will be divided by 2, and the 2 will be multiplied to this factor which I have written over here, and if you expand this factor you can write this factor to be equal to the sum of two factors, that is cos of omega q plus omega m, this whole multiplied by t plus phi q, and the second term will be cos of omega q minus omega m, then multiplied with the t, both of the difference will be multiplied by t, and then the initial phase plus phi q. So it means that now this term actually represents two frequencies. One is omega q plus omega qt plus omega mt, The second is represented by omega qt minus omega mt. So it means that the frequency of the qth mode that we are discussing now have two additional frequencies. Due to these two additional cosine functions, one would have frequency omega qt plus omega mt, that is the modulator frequency is being added, and the second one is omega qt minus omega mt, that is the frequency will from the qth order mode will be subtracted from the frequency of the modulator will be subtracted from the frequency of the qth order mode of the qth mode. But you see that I have written phi q to be the same because phi q is also over here present. Now can we change the value of phi q over here? Yes. You see that I have not introduced any phase with modulating function cos of omega mt. Here I have shown that the phase is 0. But if you add a phase term over here, for example, alpha, if you add alpha over here, that is cos of omega mt plus alpha plus phi alpha, then this phi alpha will also appear over here. And then of course the phase will be modified. So you can, this phi q which was present as an argument of the electric field representation of the q field will be modified over here. So omega mt, if there is a phase term over here, because of phi q is a phase term, which is the phase of the qth mode. But if there is a phase also present with the modulator, then that mode will also appear over here. So by changing the phase of the modulator, you can also change the phase of these two terms. Thus, equation number 1, that is this equation. So this is equation number 1. Thus, in equation number 1, EQ as a function of time also consists of two terms oscillating at frequencies omega q plus minus omega m. These are referred to as the modulation sidebands. So these are actually the sidebands. And since this is due to modulation, because if omega m is not present, then of course the sidebands modulation will not appear, because the sidebands appear because of the sum and the difference of frequencies. The sum of frequencies will be omega q plus omega m, and the difference of the frequencies will be omega q minus omega m. So it means that these are the two frequencies in addition to the original frequencies of the mode, that is omega q is present. So in addition to omega q, you have two other side bands. One side band has a frequency omega q plus omega m. The other side band would have a frequency omega q minus omega m. Then of course you see that these would represent actually three modes in the laser. One mode is operating at a frequency of omega q only. The other mode will be oscillating with the frequency omega q plus omega m, and the third mode will be operating with the frequency of omega q minus omega m. Now we want these modes. You know that we don't bother about the mode q because the q mode is the original cavity mode. The other two modes, that is omega q plus omega m and omega q minus omega m, these could be the modes which are not coinciding with the original modes of the laser cavity. You know that when we talk about the laser cavity, we have modes which are separated in frequency by delta nu. So delta nu is actually the separation between the longitudinal modes. For example, if we have the Q mode, then the next mode will be the frequency of the mode. For example, nu as of a nu Q plus delta nu, and on the left hand side we have the mode which is nu Q minus delta nu. And in terms of the angular frequencies, you can talk that we have the frequency omega Q, and you will add omega q to this one, that is omega nu. So this is delta nu, and corresponding to delta nu we have omega nu. So if you add omega q to, if you add omega delta, if you add delta omega to omega q, and if you subtract delta omega from omega q, where delta omega will be equal to 2 pi delta nu, because the 2 pi delta nu will be equal to delta omega, then you see that we have the original modes of the laser cavity. That is the next mode to the original mode of the cavity omega q will be omega q plus delta omega, and the mode to the left of this one, that is the next lower mode of the mode with mode omega q, will be omega q minus delta omega. So this delta omega corresponding to delta nu can be added to omega q to obtain the other modes. For example, you can eat plus delta omega, then you can add 2 delta omega, then you can add 3 times delta omega, 4 times delta omega, and similarly you can subtract omega q minus delta omega, omega q minus 2 times delta omega, omega q minus 3 times delta omega, and then you can get other longitudinal modes either to the right hand side of omega q or to the left hand side of the omega q. So you see that here in the description that I have given over here, that these two modes are also present in addition to the mode with the frequency omega q. So this is the frequency of the modulator. So if we modify this, if you change the omega m to a different value, you can make these two modes to coincide with the original modes of the laser cavity. Let's follow the discussion next. Now, if omega m is changed by the modulator and made equal to delta omega, and delta omega can be written as 2 pi delta nu is equal to 2 pi into c over 2l. So if you make omega m to be equal to delta omega, that is omega m is equal to delta omega, the modulation side bands coincide with the frequency of the adjacent modes of the mode q. That is, it coincides with the frequency of the q minus 1 and the q plus 1 modes. So if you add omega delta omega, you will have the q plus 1 mode, and if you subtract delta omega from omega q, you will have the frequency corresponding to the q minus 1 mode. So in addition to the mode q, you can have two other modes, q plus 1 and q minus 1. If you make this delta m equal to delta omega, and then the side bands due to the modulator will coincide with the q plus mode and with the q minus mode, which are the original cavity modes of the laser. So due to the modulator making omega m to be equal to delta omega, the two side bands of the modulator which were given by this one, that is omega q plus minus delta omega, these two side bands making omega m to be equal to delta omega, then of course the two side bands will coincide with the original side bands of the modes of the laser, that is coincides with the q minus 1 and q plus 1 modes. Thus the modulator can modify the amplitude of q minus 1 and q plus 1, which are the original modes of the laser. So their amplitudes could be modified by the modulator, because our modulator has an output has side bands which coincides with the q minus 1 and the q plus 1 modes. If such a modulator is placed close to one of the cavity mirrors, now you see that since this description is about the modulator, we want to place the modulator to close to one of the cavity mirrors. The mode coupling mechanism would lead to mode locking condition of the form, that is phi q minus 1 is equal to phi. This is the mode locking condition that we have also discussed in slide number 132, that is the previous slide. But you see that how this phi q minus 1 will come. We have the phi q and we have to subtract phi q minus 1 so that the difference become equal to phi. Similarly, if we have a phi q and if we add plus phi q plus 1, then again we would have the same phase, because we want that the difference from between the two consecutive between the two consecutive longitudinal modes or between the two consecutive modes of the laser cavity should be phi, because we want to fix the modes, because we want to fix the phases of the modes. And you know that when we fix the phases of the modes, then we say that we have done the mode locking. And the phase, this phase, from where this phi q minus 1 is coming, this will come when you introduce through the modulator a phase. For example, maybe some, for example, alpha q over here. For example, if you can, for example, you have written phi q over here. Similarly, you can add or subtract plus phi alpha or phi or minus phi alpha. You can introduce the phase with the modulator, and when you introduce the phase of the modulator, you will get the phases which will be modified over here. For example, it could be phi q plus phi alpha phi plus phi alpha, or it could be phi q minus phi alpha present or will be present over here due to the modulator, which I have not shown in the present case. So you see that that will act, that is a phase that you will introduce with the modulator. So since our modulator side bands also coincides with the with also coincides with the q minus 1 and q plus 1 modes of the laser cavity. So it means that you can change, you can set their phases also by setting the phase of the modulator as I described there, that you can introduce phi alpha or minus phi alpha, whatever you want, and you can set the phase of the those phi alpha in such a way that phi q minus, here you can write phi alpha also, or you can write phi q minus 1 to be equal to phi. This is the phase phi that we want to be fixed between any two consecutive modes of the laser. So if we have fixed the phases through the modulator, it means that we can achieve the mode locking, because mode locking means fixing the phases of the different modes of the laser cavity. So here we are talking about three modes: the central mode, the Qth mode. Not, it could not be the central mode. The Qth mode could be any mode, any Q stands for any mode. So Q mode and Q plus 1 mode and Q minus 1, Q plus 1 and Q minus 1 modes. These are the three modes that we are concentrating our discussion on, and the phases of these will be set equal to phi. That is, the consecutive phase between two longitudinal modes will be equal to phi, and this phi will be set by the phase of the modulator. Now assume that AM modulator is placed close to one cavity mirror. So we are going to place our AM modulator close to one of the cavity mirror. And you know that this is the condition that is necessary in order to do the phase locking. So this condition is necessary for the side bands of the side band due to AM modulator to coincide with the Q minus 1th and Q plus 1th modes of the laser. This condition is necessary, and if you want to set the phases according to this condition, then of course you need to set the phase of the modulator also. By that one, you can change the amplitude and the phases. We need to fix the phases according to this one, and we also can change the amplitude of the modulator by changing the value of the delta. And the modulation time period is capital T is equal to 2 pi over omega m, because omega m, you know, that is the modulating frequency of the modulator. But here we have set the value of omega m to be equal to delta omega, and you know that delta omega is nothing but the separation between the two longitudinal modes in terms of frequency. So we have 2 pi delta omega, and this delta omega can be written as 2 pi delta nu, and 2 pi will be cancelled out, and 1 over delta nu can be written as 2L over C, because delta nu is equal to C over 2L. So since delta nu is in the denominator, so we have 2L over C as a term. So this time period of the modulation should be equal to 2L over C. So you see that we are using the modulator. We have set the condition that the angular frequency of the modulator should be equal to delta omega, and delta omega is actually the angular frequency difference between the modes. That is, the modes are separated by the modes of the laser cavity are separated by delta omega. and the phases of the angular of the modulator can be set such that this condition is satisfied. So the modulation time period capital T will be equal to the cavity round trip time. You know that 2L over C is also the cavity round trip time. When the modulator produces an effect of minimum loss to the propagating modes, the light pulses pass through the modulator, and this occurs at a time Tm, which corresponds to the minimum time when the Am, that is the amplitude modulator loss, which is represented by the function 2 gamma, is minimum. This would then correspond to the steady state laser operation. So you see that in this paragraph, I am talking about the loss of the AM modulator. The AM modulator has a fluctuating loss, that its loss is varying cosinusoidally or sinusoidally with the frequency omega m, or in this case with the frequency with the delta omega. So delta omega is the frequency of the modulator, and the modulator will oscillate between its minimum value and maximum value. So when the modulator has a minimum value, it will present a minimum loss, minimum cavity loss to the propagating modes of the laser. And when the loss is minimum, then of course the output is maximum. And when the modulator has a maximum amplitude, then you see that it will present a maximum loss to the propagating modes of the laser cavity. And when the loss is maximum, then the cavity loss is maximum, then of course the output may instinct, or the output may nearly be zero. So when the loss due to the modulator is set to the minimum condition, then of course we shall achieve steady state laser operation. The loss curve will be explained next. When the amplitude modulator loss is very high, the laser output will be zero. Thus, the amplitude modulator loss periodically changes between the minimum and the maximum values. This situation is depicted in part number A of figure 1. For example, over here in this figure, you can see this 2 omega is oscillating sinusoidally. This is actually the modulator output. The modulator output is going sinusoidally. And this is represented by 2 gamma as a function of time. You see that it has minimum values and it has the maximum values. When 2 gamma function has a maximum value, it means that the loss of the cavity is set to the maximum value. Under that condition, the output will be zero. You can see that the corresponding to the maximum values of the peaks, the output over here is zero. So this is the maximum peak, the output is zero. And below the maximum loss of the peak, the output is zero. And here in the lower graph, in the lower you can see the pulses, and these are the laser pulses which correspond to the minimum value of the gamma function. That is when the modulator presents a minimum loss as a loss to the laser cavity, then of course the laser will be at the minimum loss. The laser pulse out will propagate and will pass through the will oscillate in the laser in the form of the steady state laser operation. And of course the pulses will also come out from the laser as output, and these pulses are represented by the function I of t, which is the intensity as a function of time. And Tm is the time at which the loss of the function of the or the loss of the modulator is minimum. So when the loss of the modulator is minimum, you can see that correspond to that one. You can observe the peak of the photon pulse. But you know that on this side of the minimum value, or on this side, that is on both sides of this minimum value, the loss of the cavity is increasing, And when the loss of the cavity is increasing, then of course the number of photons in the cavity are falling on either side of this peak, and due to that one, a pulse is generated in the laser cavity. So this is modulator output, and this is the output from the laser source. And you know that we have set the three conditions for the modulator, which I have explained earlier. One condition was that the side bands due to the modulator should coincide with the modes of the laser cavity. So that, and the two modes of the laser cavity which I am particularly talking is about Q-1 mode and Q+1 mode, which are located on left side and right side of the Q mode. And when the modulator modes will coincide with these Q-1 and Q+1 modes, then you can control those modes. That is, you can control the phases of those modes, and you can also control the amplitudes of those modes. For example, here we are in this gamma curve, that is 2 gamma as a function of time curve, we are controlling the output of the laser beam, output of the pulses. The pulses are separated in time by 2L over C. So you can see that T is the time period between the two minima. The time period at capital T is equal to 2L over C. Similarly, the same is the time period between the two peaks values. The pulses are separated in time by 2L over C, which is also equal to the time period of the modulator wave. The minimum of the modulator loss corresponds to the peak value of the pulses. So when corresponding to the peak value, the minimum of the modulator loss corresponds to the peak value of the pulses, which I have explained that when the loss of the modulator is minimum, then you can see that the peak corresponds to that minimum value. A pulse is allowed by the amplitude modulator. A pulse is allowed by the amplitude modulator. You can see in this case that these pulses have been controlled by the minimum loss due to the amplitude modulator. And at other positions of time, the modulator has a maximum loss, has a loss which gradually increases to the maximum value, and that wise the output of the laser in that area is 0. A pulse is allowed by the amplitude modulator when it crosses at a time the modulator presents the minimum loss. So the laser pulses will pass through the modulator at the time Tm. And Tm is the time when the modulator has minimum losses. At this time, the pulses can pass through the modulator because the modulator presents minimum loss at Tm times. The pulse can undergo one oscillation in the cavity before it reappears at the doorstep of the modulator. So you see that when these pulses will oscillate in the laser cavity, since the Tm time will open after the time period which is equal to the 2L over T, that is the time of light in the laser cavity, these pulses will reappear at the time Tm and of course will pass through the laser cavity. So the pulse then undergoes one oscillation in the cavity before it reappears at the doorstep of the modulator. So these will appear after a time capital T, which is equal to 2L over C. The situation discussed corresponds to an exact matching condition omega m is equal to delta omega. So you see that the conditions that we have discussed over here in the part A of this figure requires exact matching. That is exact matching of the frequency of the modulator. That is the modulator frequency omega m should be exactly equal to the delta omega, and delta omega is the angular separation between two consecutive modes or between two consecutive longitudinal modes of the laser. So under that condition, exactly these sharp peaks will appear when the losses of the modulator is minimum. And on either side of this one, when you see that the losses is increasing and the output has fallen to the zero values, that is a photon pulse has gone to its zero values, and between that one no other pulses will appear because the modulator is now has a maximum output, or the output which is greater, that is the loss due to the modulator is greater, and the steady state operation of the laser will be stopped. Now we talk about this one. The related paragraph will be discussed in the next slide, but here let me give you an idea what this figure is about and what this in part B. Again, you see that I am plotting two things over here. The two gamma function as a function of time and the intensity of the laser as a function of time. And I am considering and a magnified version of the above figure, because I am considering only one laser pulse and only one pattern, one pattern of the loss of the modulation loss function gamma 2 gamma. So this curve is a modulation loss represented by the 2 gamma as a function of time. This solid line is actually the input pulse which is incident on the modulator, and this dotted line is the output from the modulator, or output pulse from the modulator, or output pulse from the laser. You see that this Tm time corresponds to the minimum value of the loss in the modulator. And you know that these two pulses are slightly behind the Tm time. So when the modulator is going to at its minimum condition, the pulse that the solid pulse which occurred at the modulator is slightly behind the modulator time Tm. So you see that the peak corresponding to this solid peak, which is the laser peak oscillating in the laser cavity, is slightly below the opening time, or the below the time when the modulator is presenting the minimum loss, is slightly behind that one. And you know that look at the output, which is the dotted line. This dotted line exactly coincides with the solid line on the trailing edge. This is the trailing edge, because at the trailing edge the loss is not significant. You can see over here gamma curve is not much higher over here, but in this region you can see that the gamma function has a higher value. It means that the modulator is presenting a greater loss to the solid curve. So when the solid laser curve or the solid laser pulse. So when the solid pulse is being presented with a greater loss, then of course due to loss 1, due to that loss, the amplitude of this solid curve will fall immediately to the value represented by the dotted line. So this dotted line will then pass through the modulator. So I think that the situation will be clear, and I am now going to explain this figure, that is the figure number B in part B in the next. So this figure, which is the figure number C, will be discussed later on. So this description that I am not going to present is relevant to part B of figure number 1. Now let's assume that there is a mismatching, and that the light pulse is slightly delayed, that it is the pulse peak, that is the pulse peak occurs earlier than Tm. And you know that Tm is the minimum time presented by the loss curve presented by the modulator, where the modulator has a minimum loss. That is, the pulse peak occurs earlier than Tm. The leading edge of the pulse suffers more loss in comparison with the trailing edge. You can see that this is the leading edge of the pulse. This is the leading edge of the pulse. And the other edge, this edge is the trailing edge. So the trailing edge suffers almost very small loss, whereas this edge, which you can call it as the leading edge. So this leading edge will be presented greater loss by the modulator. And as a result, what is happening? You see that this dotted pulse has a smaller width in comparison with this broader solid pulse of the laser. So due to slight mismatching, the pulse has narrowed down in time domain. So let me read again a part of this one. That is, the pulse peak appears earlier than Tm. The leading edge of the pulse suffers more loss in comparison with the trailing edge. This is what I have explained. The dotted pulse in part B is the pulse that has passed through the modulator. So there is a more discussion about figure B. And now I am going to discuss part C here. In part C, the pulse has slightly narrowed down and the pulse peak has slightly improved its position. The narrowness of the pulse is compensated by the finite bandwidth of the gain medium, that is the active medium. And this is compensated by the finite bandwidth of the gain medium or the active medium. After many back and forth oscillations, the dotted pulse eventually attains the steady state situation presented in part A, though with a bit shortening as shown in part C of figure number 1. So you see that in part C is actually represents the output. You see, when this pulse shown in dotted passes through the modulator, then this pulse will oscillate back and forth in the modulator. And when this pulse passes back and forth or oscillates in the laser cavity, then due to the limited bandwidth of the gain medium or the active medium, you see that this pulse improves its position to the minimum value of the loss of the modulator. So coincides with so then the peak will coincide with the minimum value at the time Tm, which corresponds to the minimum value of the loss presented by the modulator. So one thing is that the position of the dotted pulse which is passing through the modulator has improved and it also now symmetric, and the second is that it has also narrowed down with respect to the original pulse that was incident on the modulator before this modulation action took place. So let me read paragraph number about the figure part C. In part C, the pulse has slightly narrowed down and the pulse peak has slightly improved its position. The narrowness of the pulse is compensated by the finite bandwidth of the gain medium. Because the gain medium, that is the active medium, has a finite bandwidth and this has improved the narrowness of the pulse. After many back and forth oscillations, the dotted pulse eventually attains the steady state situation presented in part A, though with a bit shortening as shown in part C of the figure 1. The shortening of the pulse in time domain is equivalent to its broadening in spectral domain. So this is very important point. Since we are going to narrow down the pulses in time domain, because we have the laser output I as a function of time and the pulses of light emitted as a function of time, and we have narrowed down those pulses by using the modulator, then what is its meaning in the spectral domain? The shortening of the pulse in a time domain is equivalent to its broadening in the spectral domain. And you know that spectral domain is the domain where we are talking about delta nu as the separation between two consecutive modes of the laser modes. So delta nu is actually the separation between two modes of the cavity mode. So you know that when we are shortening of the pulse, it means that we are increasing the separation delta nu between those modes. So we are talking about the broadening in spectral domain. So shortening of the pulse in time domain is equivalent to its broadening in the spectral domain. The wings of the pulse are much more attenuated and ultimately truncated. For example, according to this figure, you can see these wings. Wings mean that the points where the curves is going to join the dotted curve I am talking about. So these wings, these are the wings of the pulse. They become zero at these points very quickly, and these narrow down the pulses. The shortening of the pulse in time domain is equivalent to its broadening in spectral domain. The wings of the pulse are much more attenuated and ultimately truncated. Okay. Now we are talking about homogeneous and inhomogeneous discussion we want to carry out. So be careful and understand it very with patience, because these things are slightly tricky. In an inhomogeneously broadened line, the oscillating bandwidth delta nu L. And you know that in our previous slide, we have defined this delta nu L, that is delta nu L is equal to n times delta nu, where n is the number of longitudinal modes, capital N is the number of longitudinal modes, and delta nu is the separation in frequency between these two modes. So delta nu L is actually the bandwidth of the oscillating modes of the laser. And delta nu L is equal to capital N times delta nu, where delta nu is equal to where delta nu is the separation between two consecutive modes of the laser. So the oscillating bandwidth delta nu L approaches the inhomogeneous gain bandwidth delta nu naught prime. The inhomogeneous gain bandwidth has been discussed in one of the previous early slides. And you know that the bandwidth, inhomogeneous gain bandwidth, is represented by delta nu naught star. So this delta nu L will approach in an inhomogeneous broadened line. The delta nu L will approach the value of delta nu naught star. The amplitude modulation then actually locks the phases of the oscillating modes, because you see that when these two quantities are nearly equal to each other, then it means that the amplitude modulator then actually locks the phases of the oscillating modes. All the modes which are oscillating in the laser cavity, they have been locked in phases when delta nu L approaches the value of delta nu naught star. And this is the case we are talking about inhomogeneously broadened laser. If the modes Now, if the modes have Gaussian distribution, then we can write that delta tau prime is approximately equal to 0.44 divided by delta nu naught star. And you know that delta nu naught, what is delta tau p? This is also we have defined in the previous slide. But let me recall you, delta tau prime is actually the line width of the pulses. So if you measure the pulse, if you measure the width of the pulse at half maximum, then it will be delta tau p. So delta tau p is approximately equal to 0.44 over delta nu naught prime. And delta nu naught prime is actually the gain bandwidth, or in the inhomogeneous case of the laser. There are two pulse spectral broadening. So now I am going to discuss that the pulses in spectral domain can be broadened, and there are two reasons, because you see that here we have discussed the broadening of the oscillating bandwidth delta nu L. So how we can broaden these bandwidth, that is the oscillating bandwidth, how it can be broadened, or how we can broaden the pulse spectral broadening, pulses in the spectral domain. So there are two pulse spectral broadening mechanism, one of which is presented in part number C. That is a slight mismatch of the modulator frequency can result in a slight narrowness of the pulses in time domain. And when the pulses are narrowed down in the time domain, then it means that they are broadened in the spectral domain. So one reason has been presented in part number C. The second, pulse spectral broadening. This is not time temporal broadening, it is a spectral broadening. So the second, pulse spectral broadening occurs when the pulse passes through the active medium or the gain medium. For a homogeneously broadened line, spatial hole burning. So you see that I have also discussed the spatial hole burning in the case when I presented the case dealing with the homogeneous broadened line in some of the previous slides. For homogeneously broadened line, spatial hole burning tends to concentrate the width of the oscillating spectrum. So the oscillating spectrum will concentrate, resulting in the narrowness of the spectrum. So due to the spatial hole burning, the spectral narrowness will appear only for the case of for the homogeneous broadened line. Let us label the narrowness of the spectrum by delta nu n. So delta nu n is actually the spectrum that has resulted after the narrowness of the spectrum. So delta nu n is actually, you can see that is actually the narrowed spectrum that resulted in the case of homogeneously broadened line due to spatial hole burning. So now we can write that the delta nu n is less than delta nu naught, and you know that the delta nu naught is the case when we are talking about the mode locked laser, and when we are talking about the unmode locked laser, then we have this delta nu n. And you know that in the unmode locked laser, the spatial hole burning in the homogeneous case will occur, and then of course the spectrum will be shortened, and this spectrum is represented by delta nu n, which will be smaller than the delta nu n due to the mode locked laser. And reciprocals, you need to invert the sign over here, and then the time corresponding to this one is the tau pn, and the time corresponding to 1 over delta nu naught is represented by tau p, and tau p is the frequency, is the time at which the pulses will occur. So the temporal separation, tau p is the temporal separation between the pulses that will occur in case of the mode locked laser, and this tau pn represented in the red is actually again the separation in the temporal separation between the pulses when it is unlocked, that is when the modes are unlocked. So we can say that this period tpn is prolonged, is greater than tau p. That is the period of oscillation for mode unlocked laser, which is due to tau pn under homogeneous line broadening, is prolonged, that is greater than the time of the pulses when it is locked. The intensity profile of a mode locked laser under homogeneous line broadening is Gaussian with full width half maximum width given by delta tau p. So this delta tau p for the case of a homogeneously broadened mode locked laser is given by equation number 3. That is delta tau p is equal to 0.45 divided by the square root of nu m times delta nu naught, where nu m is the modulator frequency, because the modulator frequency that we have mentioned is omega m. So omega m is the modulator frequency in angular domain, and the modulator frequency in the linear domain is nu m. So delta tau p is approximately equal to the 0.45 divided by the square root of a nu m times delta nu naught. And delta nu naught, you see that is the gain bandwidth of the homogeneously broadened line when the laser light is when the mode locking condition is in place. So delta tau p is actually the width of the individual pulses and is given by the relationship shown in figure number 3. Now we want to modify this formula a little bit under the condition that delta nu naught prime is equal to delta nu naught. And you know that this delta nu naught prime is actually the gained bandwidth for the in the case of a inhomogeneously broadened laser. Inhomogeneous gain bandwidth was represented by delta nu naught prime. And here we are assuming that this bandwidth is approximately equal to the bandwidth for the homogeneous case. That is delta nu naught star is equal to delta nu naught. Then we can rewrite equation number 3 in the following form. You see that the left hand side has been put a label HOM, stands for the homogeneous as a subscript. And on the right hand side, I have introduced delta nu naught in the numerator and delta nu naught in the denominator. And then you see that this term can be represented as delta tau p for the inhomogeneous case. For example, this one from equation number 2, that is 0.45 or 0.44 divided by delta nu naught, because we are assuming that delta nu naught star is equal to delta nu naught. Under that condition, I can write delta tau p for the inhomogeneous case. So this has been written as delta tau p for the inhomogeneous case, and then this term is simplified as the square root of delta nu naught over nu m. But you know that delta nu naught is much larger as compared with the nu m. This is what I have written. Delta nu naught is much greater than nu m. Under that condition, you can write that the delta tau p for the homogeneous case is much greater than delta tau p for the inhomogeneous case. That is, for the inhomogeneous case, the width of the pulses will be shorter, much shorter than for the homogeneous case. So if you are using an inhomogeneously broadened laser, you can even obtain very narrow pulses, because the delta tau p is the bandwidth of those pulses, or is the line width of those pulses. When the amplitude modulator AM modulator operates with the initially mode unlocked laser, you know that even you are using AM modulator, but initially the laser initially the mode that will be incident on the modulator will be unlocked. The modulator establishes a synchronism between the oscillating modes. Mode locking establishes when one of the many noisy pulses, for example, one of the noisy pulses is shown in figure 1 of the previous slide, survives. So when one of the pulse will survive through the modulator, that is, the pulse passes through the modulator when the modulator has a minimum loss, then that pulse will survive through the modulator, and of course that will oscillate back and forth in the laser cavity, and will oscillate back and forth. The pulse that survives has its peak occurring at the time Tm, when the modulator loss is at its minimum. For high gain lasers, for example, pulsed lasers, the AM mode locking is performed using a focal cell based modulator, in which the applied voltage is varied sinusoidally from 0 to lambda by 4 voltage. Because you see that the sinusoidal oscillation will occur, and this sinusoidal oscillation I have explained will be represented by the 2 gamma as a function of time, has been shown in the figures in the figure 1 part A, B and C. However, for low gain lasers, for example continuous wave lasers, the acousto-optic based modulator is used, which has comparatively lower assertion losses. So when we are talking about the pulsed lasers, we can use the focal cell as the AM modulator, and when we are talking about the continuous wave lasers, then we can use acousto-optic AM modulator as the modulators. Now a little bit about the acousto-optic modulator. In acousto-optic modulator, the crystal is cut such that you see that this acousto-optic modulator is what I have discussed in one of the previous slides. So if you want to see the working of this acousto-optic modulator, please consult those slides. In acousto-optic modulator, the crystal is cut such that both planes are parallel with the length equal to the integral number of half wavelength of sound waves oscillating at frequency omega. So the oscillating frequency of the sound waves that we are producing is omega, and the separation between the two planes, between the two parallel planes, should be equal to integer number of half wavelengths of the sound waves that we are using. So here the standing waves of the following form will be set up between the two parallel planes, and these ascending waves can be written as S is equal to S naught cos of omega t multiplied by cos of kz, where Z is actually the separation between the two planes, and K is actually 2 pi over lambda, where lambda stands for the wavelength of the sound wave, and omega is actually frequency of the sound wave. And this equation is especially concerned is totally based on the acousto-optic modulator. The diffraction loss is modulated at a frequency of 2 omega. So the diffraction loss is modulated at a frequency of 2 omega. For this one, you need to consult previous slides and see the topics on acousto-optics in my one of the previous lectures. The loss is maximum or minimum, where the standing wave amplitude is maximum or minimum. So again, when the amplitude of the standing waves is maximum, the loss is maximum, and when the amplitude of the standing waves is minimum, the loss is minimum. The modulator must be close to one of the cavity mirrors, and the modulation frequency 2 nu or 2 omega. If you are talking about angular frequency, you talk to 2 omega. Otherwise, you talk about 2 nu must be equal to C over 2L. The transducer must operate at a frequency nu, which is equal to C over 4L. So the transducer must operate. This nu is actually the frequency of the transducer. The transducer must operate at a frequency over 4L, whereas the working of the transducer will be explained by the frequency 2 nu, whereas the transducer is required to operate at a frequency over 4L, where L is the length of the modulator. Now next we want to talk about the FM modulator. So you see that before that we have discussed the amplitude modulator, which is very popular in order to control the pulses, and now we are going to introduce the FM modulator. You know that in the FM modulator we introduce the frequency modulation, or equivalently you can say that we introduce the phase modulation. In FM modulator, the refractive index n as a function of time is sinusoidally varied with omega m again set equal to delta omega. That is omega m is equal to delta omega. Whatever modulator you use, that is you use either AM modulator or FM modulator, this is the condition that omega m is equal to delta omega must be used. And this delta omega is actually 2 pi delta nu, and delta nu is actually the separation between any two consecutive longitudinal modes. So this condition is necessary if you want to lock the phases or the amplitudes of the modulators, or the phases or the amplitudes of the modes in the laser cavity, then you must use this condition. And now this n of t is actually the refractive index variation of the material within the modulator. and these that is a function of time and is varied sinusoidally. This refractive index within the modulator material is varied sinusoidally. Under this condition, the phase modulated modes have side bands coincident with the neighboring bands. Again, you know that when this condition is satisfied, that is omega m is equal to delta omega, then you see that the side bands generated by the phase modulated, in this case phase modulated side bands will coincide with the neighboring side bands of the laser modes. The cavity modes are thus coupled and the phases are thus locked. So using FMO modulator you can lock the phases of the modes of the laser cavity. Each cavity mode then undergoes a time varying phase shift given by this relationship, that is phi is equal to n as a function of time multiplied by k multiplied by L prime, where L prime is the modulator length, lambda is the wavelength, and n of t is the refractive index of the modulator. Where L prime is the modulator length. Mode locking of the pulses would correspond either to the maximum of n of t curve or to the minimum of n of t curve as shown in figure number 2. Because you see that n of t is being varied sinusoidally by the FM modulator. So let me show you first the figure number 2. This is figure number 2. The caption of the figure is temporal behavior of the modulated refractive index n of t and the output intensity I of t in an FM mode logged technique. So this is the variation of the refractive index of the modulator within the modulator n of t, and these are the laser pulses that would pass through the modulator. So you see that I have shown these pulses in two different forms. The pulses in solid, for example, this pulse is in solid, this pulse is in solid, this pulse in solid, and the other pulse is in dotted. For example, this pulse is in dotted, this pulse is in dotted, and this pulse in dotted. So we have shown two set of pulses. And you know that one set of pulses, for example, the dotted pulses correspond to the peak values of n of t curve. So dotted occurs corresponding to the peak value of the variation curve of the refractive indices, whereas the solid curves correspond to the minimum values of the n of t curve. For example, this corresponds to the minimum value of n of t curve. This again corresponds to the minimum value of n of t curve. And in between them, there's this region where there is a variation of a parabolic variation of n of t. You see that no output is over here. So let me explain further through the previous paragraphs. So this is the phase varying shift, that introduce. Each cavity mode then undergoes a time varying phase shift according to this, where capital L is the modulator length. Mode locking of the pulses would correspond either to the maximum of n of t curve or to the minimum of n of t curve. So you know that I have explained that the two type of curves occur corresponding to the maxima in n of t curve and corresponding to the minima in n of t curves, as shown in figure number 2, which I have explained. Due to FM modulation, the cavity can be viewed as if there is no modulator. Due to FM modulation, the cavity can be viewed as if there is no modulator, and one of the mirrors periodically moves back and forth with the mirror oscillating at frequency omega m. So you see that we have discussed the FM modulator. You can also assume that the FM modulator is not present, and instead one of the cavity mirrors is periodically moving back and forth sinusoidally with the mirror oscillating at frequency omega m. The two conditions will be equivalent. That is, either you consider the FM modulator to be present close to one of the cavity mirrors, or equivalently, you can assume that FM modulator is not present, but one of the cavity mirrors is periodically oscillating back and forth towards the second mirror with an oscillating frequency omega m, and omega m is equal to delta omega. The maxima and minima of n of t correspond to the cases when the mirror is at extreme positions. That is, the mirror is either closest to the second mirror or farthest away from the second mirror. Just about the extreme positions, the pulse undergoes either positive or negative parabolic phases variations, which respectively result in solid or the dotted pulses. This results in broadening of the pulse spectrum, which is compensated by the spectral narrowness when the pulse passes through active medium. So active medium do the compensation that it narrows down the pulses slightly and compensate the broadening due to the parabolic phase variations. The switching of the pulses in the two modes, solids or dotted, makes the FM technique impractical. So you see that in the FM technique, as I mentioned earlier, that two types of pulses can oscillate within the laser cavity, and two pulses, that is the solid pulses and the pulses in dotted, will come out also as an output from the laser source, and also these two pulses, these two types of pulses will also oscillate within the laser cavity. And due to the presence of these two types of pulses, the FM technique is impractical. Focal cell based electro-optic phase modulator is used for FM modulation. So you can use the focal cells as an FM modulator. The focal cell is oriented with its axis parallel to the polarization of the incident beam to avoid beam rotation. Because if the axis of the focal cell are not parallel to the polarization state of the incident beam, then of course the polarization rotation will take place and we would not be able to perform the FM modulation. For the focal cell to perform the FM modulation, it is required that its axis should be parallel to the axis of the incident beam, polarized beam, to avoid any beam rotation. The beam, however, gets phase modulated when the focal cell is sinusoidally modulated. So you see that in the FM modulator, here we are rather talking about the frequency modulation. We are talking about actually the phase modulation. So this is the end of slide number 133.